Bismillah ar-Rahman ar-Rahim. Welcome to Tahar Scholar. We are الجمعة 15 ديسمبر 2023 or in English Friday the 15th December 2023. So we are still in our series programming with Matlab. We have seen in the five previous practicals how to manipulate data types, matrices, strings, structures, and cells. And we have also seen how to write a script and a function. In this practical, we focus on algorithms. That is, to understand an algorithm, to implement it, and to test it. I have prepared for that a series of 3 exercises. So let's take a look at it, and then we solve it. I will use also a pen and a paper to explain the algorithm. Then I switch to Octave to implement the algorithm. So we will use 2 settings, my notebook and my computer, Octave on my computer. So let's take a look at the series. So this is series number 1. There is only one series for this appendix, Programming with Matlab. It's a long appendix. Actually, it can be seen as a short course or crash course for Matlab. For those who have never seen or studied Matlab, or have studied it superficially, not in depth. And we need that for our module. This course, the main topic, the goal of this course is numerical methods, but Matlab is important in practicals because we use it in practicals. So Tahar Scholar channel, copyright 2023, Tahar Jawad. I have written it in the 2nd December 23. So exercise 1, there are 3 algorithms. The first is about sorting a vector. Write an algorithm that sorts a vector in an ascending order. For example, the following vector becomes, after sorting, the following one. So the first element is the minimum, and the last element is the maximum. And they are sorted in ascending order. And the second exercise is about prime numbers. Write an algorithm that checks whether a given integer is a prime number. Let us recall that an integer is a prime number only if it is divisible by 1 and itself, and by no other number. So it has only 2 divisors, itself and 1. For example, the following integers are all prime numbers. These are the first prime numbers: 2, 3, 5, 7, 11, 13, 17, 19, etc. Observe also that all prime numbers are odd numbers, with the sole exception of integer 2. 2 is, of course, an even number, but all the rest are odd numbers. So we are asked here to implement an algorithm to check whether a number is a prime number or not. The third exercise is about Elkarkhi's triangle and binomial expansion. This is also in literature, in Western literature, is known by Pascal, Blaise Pascal, a French mathematician. But actually the author is Elkarkhi, Abu Bakr Elkarkhi, in the 10th century, while Pascal is in the 17th century, about more than 600 years later. So the first mathematician to devise or study this problem is Elkarkhi. So let's read the exercise. Abu Bakr Elkarkhi's triangle is a triangle of integers built in such fashion that its coefficients could be used to calculate a binomial expansion of any degree. For example, the following binomial expansion of the 4th degree reads, so x plus y all to the power of 4, x to the 4 plus 4 times x cubed times y plus 6 x squared y squared plus 4 times x y cubed plus plus y to the power of 4. The degree is always 4. 1 plus 3, 4. 2 plus 2, 4. 3 plus 1, 4, and so on. In each term, the degree is always 4, but spread between x and y. And the Elkarkhi triangles of the same order is the following triangle. You can see the fifth row corresponding to order 4. The order starts from 0 to 4. This is the fifth row. First, second, third, fourth, the fifth row. The coefficients of the fifth row are the coefficients of the binomial. That's actually a theorem that has been proved by Elkarkhi in the 10th century. So, what is the question? Study the pattern of the triangle of a given order n. This is just an example, but you should deal with any order, a triangle of any order, and write an algorithm that generates it. Then the second task, use it to calculate, for example, 1.5 to the power of 4. We separate 1.5 to 1 plus 0.5 to the power of 4. Of course, this is just an example. The algorithm we will write for the binomial should work with any x and any y and any n, any degree. But this is an example. So here there is a short historical note, because often in textbooks they don't talk about Abu Bakr al-Karkhi. So Abu Bakr al-Karkhi, or in Arabic Abu Bakr al-Karkhi, 14th Hijri century, 953 or 953 to 1029 CE. So that's about 10 to 11, about 10, more than 10, about 10 centuries ago. He's an Arab mathematician and engineer. Actually, most of his work is in Baghdad. He is the first mathematician to discover and study the binomial theorem. The binomial theorem relates this expression to this triangle, the coefficients of the triangle to the binomial. This is the theorem. He is also the author of several books and treatises. The most important ones are الفخري في الجبر والمقابلات، البديع في الحساب، إنبات المياه الخفية. الجبر means algebra, and المقابلات means equations. So he has a book on algebra and equations. الحساب means arithmetic, another book on arithmetic. And the last one, المياه الخفية, means the hidden water, how to extract hidden water. So he has also work on hydrodynamics, maybe one of the first work on hydrodynamics. He left mathematics to work as an engineer in his when he became older. So the original treatise on the binomial theorem was lost, but excerpts from it have been reported by several Arab mathematicians of that era. So that's the series. Let's go to our setting with notebook. We explain the theorem. We explain the algorithm, how we sort a vector. There are several algorithms, but we will choose one simple one. We study it, and then we come back to our setting, computer setting, and solve the exercise. So let us focus on exercise 1. We have seen 5 practicals, and this is the 6th practical. It has 3 exercises. The first exercise is about sorting a vector. So let us draw a vector, any vector, but of 8 elements, for example, to design our algorithm visually. So the vector u, let's call it vector u. And let us suppose we have sorted the first, the second, and the third element, and we are in the ith element. I is generic; it can be 1, so we are sorting the first element. If it is 2, we are sorting the second element, and so on. It is generic. It can be from 1 till the last element. So these elements are not sorted, are not yet sorted. This is a simple algorithm. It is based on the following observation. The minimum at any subvector from I till n must be at the first position. So here you must have the minimum among the elements that have been sorted. These one before I are already sorted. These are sorted. We are not modifying them. They are at their right position. Sorted elements. These are sorted. So we look from I till n in this subvector. We look, this is the subvector u from I to n. We look the minimum. Let us suppose we have found it here. So 1, 2, 3, 4. We have found it at the 4th position from I. This is the value, the previous value in I, and this is the minimum in the subvector uin. Let's define here its position. Let's call it I mean, and its value u mean. This is the minimum value in this subvector. What we do, we swap. What was in I mean become here, and what was in I become here. Because that's what we want. We want the minimum value to be at the first position in the subvector, uin. uin. And that's it. But there is 2 cases. There is a special case, an edge case. It could happen that the minimum is already at the first position in uin, in the subvector uin. So the case where I mean is already equal 1, we do not swap. It is at its right position, no swapping. But the general case, when I mean is different from 1, we swap. But here you have to be careful because I, the index I, is in the vector u, in the mother vector u, not the subvector. While I mean is in the subvector, this is the 4th element in the subvector uin. So we have to update I minimum, we have to update it by adding the number of elements that have been already sorted. So what we do, we increment. Plus equal means increment. You add the operator, it is 2 operators actually. Plus equals means you add the right value here, right hand value to the current value. You increment it. And minus, you decrement it. Plus equal I minus 1. I minus 1 is the number of elements sorted. And then you swap. You swap means you take the value before to erase ui. So what we will do, we put at I mean the value at the index I in this cell, and we change the value in I using umean. And that's it. That's the swapping. in the case where I mean is different from 1. And we do that, we repeat this from I equal 1, not till the last, because when we reach the last, it is already sorted, because we have sorted all the elements before it. When we reach n, I equal n, there is no other elements afterwards to sort. There's only one element, so it's de facto sorted, already sorted. So I must go from 1 till n minus 1, n moins 1 in French, till n minus 1. And another important, so this is the algorithm. We look for the minimum, its position and its value, and then we swap in the case that I mean is not equal 1. And before to swap, we should update the value of the index to be the value of the index in the vector U, in the whole vector U, not in the subvector UIN. Because the search of the minimum is carried out in the subvector UIN, not in the global vector. That's why should be careful with the index. How we calculate the minimum? We have a function. We have already seen it in built-in function in Matlab called minimum. So we give it the subvector from I till n, and normally it returns the minimum. If you give it one variable, it will set it to the minimum. But if you give it two variables, let's write like this: I minimum, U minimum, the value, and then its index. If you omit the index, it returns only the minimum. But if you give two variables, it will set the value first and then the index. This is a built-in function. So we do not have to, fortunately, we do not have to write it to reinvent the wheel, because it's already there. And that's one good thing in Matlab. There are many, many built-in functions that help you in writing your algorithms. So we look for the minimum, which function we can use. We use the built-in function minimum. And that's it. Let's, before to go to the computer and implement it, let's test it. We have a vector. We have given a vector v equal 1, 0, 5 minus 1.2, 2.8, 5.7, and 0. So we have vector 1, 2, 3, 4, 5 elements. Let's test our algorithm on this vector. So I equal 1. We start with I equal 1. And we look from I equal 1 till n in the subvector here is the whole vector. We look for the minimum. When you look for the minimum, you go from I till n. So I equal 1 from 1 till n. And here is 5. I mean 6. Is 6. Which one is the minimum? Negative. It's minus 1.2. So we have here I minimum equal 3 and U minimum equal the value minus 1.2. Then what we do, we swap the value here becomes here, and the value here becomes here. We set first u mean, because if we set ui first, we will erase the value in this box. So we first change the value here 1 and then -1, 2. So we have here -1, 2 and here 1, and the rest will not change. The rest will not change. 5, 7, and 0. So this is for I equal 1. Let's now do for I equal 2. So this one is already sorted. This one is already sorted. We are in the second. Let's look for the minimum from 2 till 6. 0, 5, 1, 2 point, it's 0, which is at the at the 5th position, not in the vector V, in this subvector, from 2 to 6. So what we get, I minimum is at the 5th position. Now be careful with that, and u mean is 0. So we have first to update the index to be such that the value be indexed in the global vector, in the main vector or the mother vector. So what we do, we change I mean plus 1. It becomes 6. And we swap the element in the 6th position with the element in the 2nd position. The 6th element and the 2nd element will be swapped. And we get the vector so 0 become here and 0, 5 become here. And the rest is unchanged. So 1, 2.8, 5.7, and the first, we will not modify it. It's already minus 1.2. And we continue, I equal 3, etc. I equal 3, etc. So we have, for I equal 1 and I equal 2, we have sorted 2 first elements. The rest is not yet sorted. We continue till I equal 5. That's the algorithm is very simple. There are other algorithms more sophisticated, like quicksort and merge sort. We will come back to the performance later, but let's first practice this, what we have written here. Let us practice it in on Octave. Okay. So we are back to our computer setting. This is the function sort. We have already saved it in a file sort, and as you can see, the input is the vector u, and the vector to be sorted, and the output is the same vector, because it will make a copy of the given vector, the argument you give it to the function. It will sort it, and then it will return it, because it is a copy actually to the argument. If you do not return it, the copy will be lost after after the call to the function. So you have to return it. And this is general. If you want to modify a value through a function, you must return it, because the function will work only with copies of the arguments, as I explained it in previous, I think in the previous practical. So you cannot here give a reference. Say, for example, here like this, you say reference to the vector u, and you sort the vector u. It will not work. It will sort the copy of the vector u. I mean the argument you give to the vector. It can be u, v, w, any vector. So you must return it once you sort it. Then here is a comment. Sort a vector in ascending order, TAR Scholar programming with Matlab. So this is for TAR Scholar channel, practical 6, algorithms by TAR Jawad, the date Algeria. The first thing to do, we store the number of elements in n, and then we have our loop. I goes from 1 till n minus 1. That is, we will sort the first element till the element just before the last, because the last will then be sorted. What we do for each I, we look for the minimum in the subvector uin, as I explained on the notebook. And the function built-in mean, return the built-in function mean, return the value you mean, and I mean the position. The position, the value, and the position of the minimum in the subvector uin. And in the case I mean is not equal 1, that is the current value of I, the value at the current index at I is not the minimum of the subvector uin. In that case, we have to swap. But before swapping, we update the index I mean by incrementing it with the number of elements sorted, and then we swap ui mean and ui. And that's it, very simple, very easy. That's, we have made a modification here. Okay. We save it, and we need a script to test our function. So I have already copy-pasted, I think, yeah. Okay, so we need this script, programming with Matlab, sorting a vector in ascending order, and the usual the author and the date. We clear all what is in the memory, and we clear the console. Then we have the vector v. I called it on purpose v to be different from u, because this is the parameter. This is called the parameter, u is called the parameter, and here is called the argument. It will copy the argument, will sort the copy of the argument, and then we return it. So the vector v, we print it using num2string. We have already seen num2string. We use it to format a matrix. We use a format 10.2f, floating point. And if you have forgotten, or you have not yet studied practical, I think practical 5, no, practical 4, practical 3 and practical 4 in this series are dedicated to strings. So if you have not yet studied them, please check them. And then we call our function sort the vector v, and we save it either in v itself, we modify the original vector, or we can store it in another vector w. And then we print it. We print it like this, using the same function. But there is a function, a built-in function in Matlab called isSorted. It will check if is sorted. It will check if our vector w is actually sorted, is indeed sorted. If our function sort phase is sorted, will return false. But if it is correctly implemented, it is of course correctly implemented, then it will return true. So is sorted, any vector you give to it, it will check it. If it is sorted, it will return true. Otherwise, it will return false. So it's a handy function to use here. and we print our vector W and if. And if. So here it's not V, but W, and here is W. Here is V, yeah, not U. Made a mistake. Okay. So that's it. We save it. We call it, I usually, when I test the function, I usually use project, and then the name of the function. So I know that proj sort is a very simple script to test my function. And I give it a number, 0, 1, because later I can modify it or add another idea, etc. So first version 0, 1, and I save it. And then I push the button, the run button, and I see in the command window, yeah, it is sorted. We have seen in the notebook the first two elements when we tested the algorithm, and as you can see, yeah, -1, 2, and 0, as we have seen in the notebook, and the rest using the algorithm. It can sort, of course, any vector. For example, let's check another vector. Let's call it big V, and let's set it with random numbers from a row vector of, for example, 8 elements, randomly generated between 0 and 1. Okay. And we call our vector again, big W, our function, I mean, capital S sort, and the vector V. And as you can see here, they are sorted. You can see also that visually, if the vector is sorted or not, using a function called bar to draw that. We call bar vector V, let us bring our window here. So this is our vector before sorting it. Okay, randomly generated. Now after sorting it, bar W, we have not sorted yet. Enter. I haven't typed enter. Okay. Check again. Yes. As you can see visually, they are sorted. So function bar is handy to check also. You can draw both the two bars in the same figure using subplot. And I want with one single row, I want our figure with one single row and two figures, two plotting. And the first index will go for bar V. Okay, enter. And so here we have actually the place of two plots in one row. This is one row and two columns. It's like a grid. You have parted your figure in a grid with one row and two figures. This is the first figure because we have used the index 1 and then index 2 for W, the sorted vector. And let's check our figure again. We have it. So this is before, and this is after the call to function sort. Finally, before to finish this exercise, there is 2 points. The performance, we will see it on the notebook. And the second thing is the built-in function sort. There is a function sort called sort with small s. not big S. Big S is our algorithm, but small s is a built-in function that uses a more complex algorithm. And in general, built-in functions are written not in Matlab, are written in Fortran or in C language, and they are very fast. So in the real world, better use, of course, built-in functions. But here we are learning how to sort a vector. That's why we have implemented our own function. But we can also, for example, here W2, we can also use the built-in function sort, and we get, of course, the same result as here with small w. So exactly the same. Let's now go to our setting with a notebook. In this section, we study the performance of our algorithm. That is, in this case, how many comparisons we make to sort all the elements in the vector. So we have the vector u. Let us suppose we have already sorted the first elements, and we are in the ith element. We want to sort the ith element. And we have seen to do that. In order to do that, we look for the minimum in the subvector u from I till n. We look for a minimum here using the function min. The function min, when it has as argument in, it performs comparisons to look for the minimum. It compares this element with this element, and then the element with the current minimum, and then the other element, and so on. It compares each element with the current minimum. So how many comparisons we have? We have the number of elements in the subvector minus 1, because the comparison is always between two elements. So if you have two elements, there is one comparison. If you have three elements, there are only two comparisons, and so on. So the number performs n minus I comparisons. So the cost here per operation, per each iteration, is low. It's just a comparison. It's not a call to a function or a more complex operation. So the operation has a low cost, but we are interested to understand or to find how many comparisons we have to do in order to sort all the elements. We have seen here only the ith element, but what about I equal 1, I equal 2, and so on? So for example, let us do that. Here for I equal 1. We want to sort the first element. The first element, I equal 1. How many comparison we have to do, or how many comparison the function min has to do to find the minimum? It will do n minus 1. So we have n minus 1 comparisons, n minus 1 operations, plus I equal to n minus 2 operations, and so on until the last element in the loop. Our loop starts from I equal 1 till I equal n minus 1, because the last element will be already sorted when we reach it. So we sort only from 1 till n minus 1. when I equal n minus 1, how many comparisons? We replace I here. It's obvious it's only 2, but let's replace it here. We have n minus, this is when I equal n minus 1. This will lead to n minus 1. That is one operation, one comparison. There is only one comparison. Compare this one with this one, because all the other elements have already been sorted. So we have one operation. And before it, 2, and 3, and so on. So it decreases by a step of minus 1 from n minus 1 till 1. And this is called, what is called this? What we call that? An arithmetic sequence. This is an arithmetic sequence of n minus 1 terms. And we know from calculus, let's write it here, arithmetic sequence. We know from calculus that the sum of an arithmetic sequence, it equals the first term, n minus 1, plus the last term, 1, by the number of terms, n minus 1, divided by 2. So this is the first term, and this is the last term. Any arithmetic sequence, whatever the step is, here it is minus 1, whatever the step is, last term, and here the number of terms. You can check any textbook in calculus, first year in the university. So, which give us n minus 1 plus 1, it's n minus 1 over 2, which is equal to n squared over 2 minus n over 2. This is the number, the total number our algorithm do, total number of what? Of comparisons that our algorithm has to do in order to sort all the elements from I equal 1 till I n minus 1, the loop 4. So this is the total, this is the cost of the algorithm. And actually the cost is important when n increases, when n is large. When n is large, this is the most important term. The other terms are neglected. And we take the term with the highest exponent, n squared. So for example, if n equal 1,000, this becomes 1 million. And this is 1,000. 1,000 is smaller than 1 million, of course. 10 is smaller, 1,000 times smaller. That's why when n is large, we say that the order of our algorithm, I mean not the order, well, we call that the time complexity. The time complexity is of the order n squared over 2. This is called the time complexity. The time complexity. That is the time complexity here, how we can also express it, how much it will take us to sort the algorithm. How many comparisons, because the comparison is the main operation of the algorithm. how many comparisons it takes us to sort all the elements from I equal 1 to I n minus 1. We call that the time complexity. It measures the number of iterations done in the whole algorithm. So the time complexity is of the order of n squared over 2, when n is large. And this is huge. This is not a good algorithm in terms of time complexity. But it is simple, easy, pedagogical, which is our goal here in this practical. There are other algorithms more complex and faster. I am aware of two algorithms. There are others, not many, maybe 4 or 5, but I am aware of two algorithms to sort a vector or a sequence of elements. So a quick sort, first is called quick sort, and the second is called merge sort. And their time complexity, that is the total number of iterations to perform the algorithm, to sort the vector. Time complexity is between the order of n logarithm of n. And the worst case, this is the best case, and the worst case is n squared. So this is the worst case, and this is the best case. It depends of the vector, of the elements, of the input, of the data. It does not only depend on the algorithm in this case. It depends also of the data. So this is the best case, and this is the worst. And generally, it is more close to the best case. So they perform n log n, of course, it is smaller than n squared over 2. So they are better than our algorithm. And actually in Matlab, the function sort that we have seen just now in our computer setting, function sort with small s uses quick sort, the algorithm a quick sort. This is in Octave. I'm not sure about Matlab, the Fission Matlab. So sort uses quick sort algorithm, and it's not only the algorithm, it's also the implementation. It is implemented and is implemented in C. It is implemented in language C, which is, of course, the code compiled with C is, of course, faster than a script language, any script language. When you compare with a compiled language, of course, it's far faster, sometimes 10 to 100 times faster, particularly when you use a loop. So that's it for the performance. We have studied the time complexity of our algorithm. So let's move to exercise number 2. So for exercise number 2, our goal is to check whether a given integer is a prime number. So we start with the algorithm. The algorithm, well, the first version of the algorithm is very simple. To check if an integer is a prime number, we try to divide n by all the integers from 2 to n minus 1. We try the division from 2 to n minus 1. If any integer in this range is a divisor of n, then n is not a prime number. So how we do that? There is a function called moduli, mod, and it gives it returns the remainder of n, the division of n by I. Two numbers, the division of two numbers, the remainder is given by moduli. So if we use it for n and I, with I from 2 till n minus 1, we get the remainder. We get the remainder of the division of n by I. How to write that in Matlab? Very simple. We use a loop for I from 2 till n minus 1, and inside the loop we check if the modulo or modulus of n by I equals comparison, not assignment, equals 0. That is, I is a divisor of n. If the remainder equals 0, means I is the divisor of n. Then what we do, we use a variable, I call it prime, I prime. It is a Boolean variable, it takes true or false. So if the remainder is 0, it is false. The number cannot be, n cannot be a prime number. So it is false. And we break the loop. Not just we break the loop, we finish the function. We have finished the task. So I don't use a break, I use a return. And if. We have not to continue. If one single integer between 2 and n minus 1 is a divisor, then n, according to the definition, a prime number, n cannot be a prime number. Otherwise we continue. We loop all the integers. If no integer from 2 to n minus 1 is a divisor, then and 4, then I prime equal true. So the result of our function is stored in I prime. It is false if n is an integer, and it is true otherwise. So this is the algorithm. It's very simple. It is a loop for, and we use the built-in function moduli or modulus of n by I. But this is not efficient, of course. We have not to cross actually all the integers between 2 and n minus 1. All the integers that are smaller than n and greater than 1. There is another algorithm, another version, well known actually. So it is based on the fact that n can be decomposed, any number, any integer can be decomposed into integers, except prime numbers. So if n is not a prime number, then there exist two integers xy in the range 2 to n minus 1, such that n equal x and y. This is the first divisor, and this is the second divisor. Any integer, except prime numbers. Prime numbers actually cannot be decomposed, and any other number can be decomposed into other integers. And we can check that if x is less than or equals square root of n, then y is greater than square root of n. If one divisor is smaller than square root of n, then the other is greater than square root of n. Always, always. So we have actually subdivided the range from 2 till n minus 1 in two sets. A smaller set that goes till square, that ends by square root of n, and another larger set from square root of n till n minus 1. Here means not included. And the other set is from 2 till square root of n. There is, of course, a special case when x is equal to y, and both are equal to square root of n. That is, n is a square of a number. This is a special case, and of course, it will belong to the first set. So our test here, we test the integer, the divisors. We test any integer to be a divisor only in this set, not in the whole set, only in this smaller set. Because if there is no divisor, there is no x belonging to this first set, it is impossible that there is a y divisor or the second divisor belong to the second set. If x is not here, then y also is not here, and hence there is no divisor, because this is a theorem. This is a theorem. If one divisor belongs to this set, then automatically the other belong to the other subset. Square root of n separate the two divisors. We can prove that very easily. If x is smaller than square root of n, then we can multiply by y. Y is positive, so xy square root is less or equal than y square root of n. But what is this? It is n. So we have n is less than y square root of n. And if we simplify square root n, we get square root of n less than or equal y, which is equivalent to y, bigger or larger, greater than square root of n. So we have actually two disjoint sets. When the first set contains the first divisor, and the second set contains the second divisor. If the first set is empty, then automatically the second is empty. xy cannot be both in the second set. So our algorithm becomes the following. For I, from 2 till square root of n is a real number. So we get only the integer part of n. We use a function, another function, built-in function called fix. I've used here modulo, and here we use fix. For integer, for numbers, real numbers, for example, for 3.7, round will return 3. Let me check. So, for example, for 3.7, round will return 4, not 3. Seal will return 4 also, the largest number, the smallest integer that is greater than 347. which is 4. And the floor, the largest integer that is small than 3.7, which is 3. Trunc is not in Octava. I'm sorry, yeah, truncation, but fix will return. I think trunc is in C or Fortran, but not in Matlab. I just checked. And fix return the integer part. So it returns 3, the integer part. This is for built-in functions that deal with a real number, convert a real number to an integer. So we have used here 3.7. You can check any real number, 3.2, 3.5, etc. So we use fix square root of n. Square root of n. And the rest is the same. That is, if modulo of n by I equals 0, then I prime equal false, and we return. We do not break, we return, and if. We finish the function. And in the end, after the loop 4, if it passes the loop 4, all the tests, and we get I prime equal true. Here be careful how we use return. If we use break, it sets I prime equal false, and then it jumps here and sets I prime equal true, which is of course false. So we have to return. We have finished. We have not to continue our algorithm. It is the number cannot be an integer, so we return. It cannot be a prime number, so we return I prime equal false. I prime equal false. And that's it. We have changed the boundary of our set. We have reduced substantially our set from 2 till n minus 1 to square root of n, which is an important gain of performance. But we can do further. So let's move to the third version. So in the third version, let us observe that a prime number, if n is a prime number, it is impossible that it is an even number. It cannot be an even number. Is a prime number can never be an even number. Except 2. So we do not have actually to test if an even number is a divisor of n. We just test if 2 is a divisor of n. Because if 2, let's write it here, if 2 is not a divisor of n, then no other even number can be a divisor of n. No other even number. For example, if 2 is not a divisor of n, then 4 cannot be a divisor of n, of course, because it contains 2. 4 is 2 by 2. So if 4 is a divisor, so 2 is also. So is 2. 8, 6, 9, 10, etc. 8 is 2 by 4. 10 is 2 by 5, and so on. So we do not have to test if n is a divisor by 4 or by 8 or by 10. We skip them. We sift the even, we say that we sift even integers. And hence our loop becomes like this. For I equal, we use a vector here, we test first 2, and then we start from 3, and we jump to 5 and to 7. So the step here will be 2. We avoid, we skip, we sift even integer, because we test here 2, if it is a divisor or not. If it is a divisor, then we stop the loop. It is not a prime number. If it is not a divisor, we do not have to check the even with the even number. We do not have to check if 4 is a divisor, if 6 is a divisor, if 8, and so on. So we skip them using the step equal to, not equal 1, the default. And the boundary is the same, fix square root of n. So very slight modification, and we finish, of course, a vector here. So I will cross this vector, it has 2, and then all the odd integers that are smaller or equal square root of n. And inside the loop, the same thing. If modulo of n I equal 0, that is, I is a divisor of n, then I prime, exactly what we have done before, is false, and is false, and we return. We have finished the test. It cannot be a prime number, and for, and if, and if. And here, and for, and I prime equal true. And this is our final version of testing. Let us call it isPrime. isPrime. We will store it as a function in isPrime. And so this is the trick here. Let's emphasize that. And that's it for our algorithm. Let's before to go to the computer setting, let's see 2 points. The first point is the performance. So performance. Performance is the number of iterations. Per each iteration, the cost is very low because we use modulus. So the remainder of division of 2 integers is very fast. It's very fast operation. What is important here is the number of iteration. So the time complexity is of the order of square root of n divided by 2, because we skip or we sift even numbers. We check only odd integers, with the exception, of course, of 2. So it is of the order of square root of n over 2, which is really fast, because actually if you make difference of square root of n minus n over 2, so you compare square root of n to the half of the range 1 till n. In this range, you compare square root of n minus n of 2. You draw this function with this function of n. You get a curve like this. This is 1, this is 2, 3, and 4. It passes by 4 and by 0. If we replace here 4, we get 0. If we replace 0, we get 0. And we get a parabola like this. And then it decreases parabolically. The difference decreases parabolically, become very small. This is n. So square root of n is very small compared to the half of the range. So that's why this order of complexity is very good. It's very good algorithm because it decreases substantially when n increases, when n is large. And let us make a test here, third point. Let's test our algorithm. Testing the algorithm. We check a sample, for example, n equal 97. We deduce that square root of n is, so the square root of n is 9849, approximately. And its integer part is 9. So we check I inside the set 2, 3, 5, 7, and 9. Start from 3 till 9. From 3 till the boundary, the integer part of square root of n. And we skip even numbers. So we add 2, 3 plus 2, 5, 5 plus 2, 7, 7 plus 2, 9. And always we check first of all to check if a divisor is an even number. If it is not, then we check all the odd numbers till square root of n. So it's a very small set. It contains only 5 elements. Instead, so I is in this set instead of in the first algorithm, instead of 2, 3, 4, 5, etc. till 95, 96. If you do some calculation, you find that this set is 5% of this set. So the performance is huge. And that's it for our algorithm. Let's go to the computer setting and see how our function works. We will test it with a script. So our function is isPrime. We have stored it in the file isPrime m. It gets as input n, the number we want to check if it is a prime number, and it returns a Boolean variable I prime, which will be equal to true if n is a prime number, otherwise it will be equal to false. Check whether a given number is a prime number. Tahar Scholar, Programming with Matlab, Practical 6, Algorithm by Tahar Jawad, and the date and Algeria. I written it in the 7th December. So the first command, we check whether n is an integer. So the number of element in n is 1. It's not a matrix. And the integer part of n is n itself. So n is an integer. Otherwise, this will be false. So it's just a small test to check that the user is using an integer, not a real number. And then we exclude all the integers that are less or equal to 1. They cannot be prime numbers. 1 is not a prime number. And there is an exception for even, as I said before, an integer cannot be an even number. with the only exception n equal 2. So if n equal 2, I prime equal true, and we return. We finish our test. Then we do the loop. 2, we test if 2 is a divisor, and then all the odd numbers till the integer part of square root of n. If modulo n by I equals 0, then I prime equal false, and we return. Otherwise we loop till all the integers have been tested in this vector. They are not divisors of n. So I prime equal true, as I explained in the notebook setting. Now let's test this function. So as usual, we build a script. Let's call it, I will use copy paste before to call it. So I copy paste. This is our script. So a comment, programming with Matlab, practical 6 algorithms, checking whether an integer is a prime integer by Tajwad, the date, and Algeria. We clear all what is in memory, CLC, clear the console, then we use a sample of integer. We use rand I. Rand I will generate a vector of integers randomly generated, and that are less than n, big N, and the size of our vector, it's a row vector that contains m element. N and m are given by the user. So we ask to input big N, and then we ask to input m. N primes up to n. So all the primes generated will not exceed n. And m is the size of the vector, as I said. And what we will do with that, we will test each element. So let's write here, testing isPrime function isPrime. Okay. What we will do, we will apply isPrime to every element of U using array function. We have already seen that vectorization, I think in practical 5. We call the function isPrime. Our function isPrime. Okay. And the vector U. It will apply isPrime to every element of U. It's like we have called isPrime U I. For I equals to 1, from 1 to the length number of element of U. This is what array function do. So instead of doing a loop for, it is better to call here array function. And it will return a vector containing the result of the application of isPrime. So it is true or false, or 1 and 0. True and false are stored as integer. True is 1 and false is 0. So we save it in I. And let's see what we have. Let's save it first. Let's call it proj isPrime, or project primes. Project primes. Project primes. Project in French. Project primes. And we save. And we test. Let's see what before, let's say less than 100. So we want to generate integers that will not be greater than 100. And our vector should be less than 100. So let's say 20. And we get, I have not printed the U. Okay. U first, and then I. So 57, false. is not a prime number. 61 is a prime number. And it applies then isPrime to 18. 18 is not a prime number. 0. 67 is a prime number. 1, and so on. So we have a vector that contains only 1 or 0. 1 means it is a prime number, and 0 means it is not a prime number. We would like to extract the prime numbers from here. How we do that? We use a function. We use a built-in function called find. Find. Another built-in function called find. And it takes as input a vector containing 0 or 1. It returns the indices of those numbers that are different from 0. So this is 1, this is 2, it returns 2. 3, no, 4, it returns 4. So it collects the indices of those numbers that are different from 0, which are actually the prime numbers. Let's check that. And as you can see here, the second element, the fourth element, the sixth element, the 10th element, the 12th element, and so on. And we will use these indices with the vector u to extract the value of these numbers. So let's write here u find I. And this is our prime numbers. And that's it. Let's write that here. So let's collect our prime numbers in V, and we use the function find to collect only those numbers that are different from 0 in the vector I, and we get all our primes. And we let's display u, then I, and then V. And that's it. And we return another sample, 120. And as you can see here, this is the vector u, and this is the vector I, and this is the numbers. The display is not is a little bit ugly. Let's change that. I have already written that, so to save time, we copy paste. We use the function printf, and we use the same format 5i. So the length of each integer in 5 characters. And let's save and print it again, and check it again. 120 and OW. Sorry, yeah, I called it W, not V. It's okay. We change it. We save and we return again. 120. And as you can see here, we have generated a vector of integers randomly generated less than 100. And this is the indices of prime numbers, the numbers that are primes. So 19, 31, and 1. All the rest are not primes. And we have collected them here again in a vector V, 19, 31, and 3. In Matlab, there are also functions, built-in functions that deal with prime numbers. The first is isPrime. isPrime, it works like our function isPrime, but it can also take as input a vector, a whole vector. Then it will return a boolean, true or false, for each entries. For example, isPrime of 2 till 10, it will return a boolean vector because we have given it a vector, not an integer. While isPrime, our isPrime, takes only an integer, like for example 7. It will return only one single boolean. The second function is primes, a built-in function called primes. It returns all the prime numbers up to a given number. For example, primes 10, it will return 2, 3, 5, 7. All the prime integers that are less than or equal 10. Primes 100. And as you can see here, all the primes till 97. Less than 100. And that's it for exercise number 2. I think we have to stop here. It's already a long video. Exercise 3. We will do it in. We will solve it in a separate practical, in the 7th practical. So see you inshallah in the next practical. Peace.